Okay, we got a recording going. That's good. Let's see. MATLAB. Excuse me. All right. Ready to go. Oh, great. Out-of-date license. Update. Complete. Oh, good. Okay. Now it makes me restart MATLAB. It's probably going to want an update in MATLAB, but I don't have time for that right now, so. All right. Let's take a look at where we're at today. Programming, problem solving. So we are, excuse me, at the point of week. So last week was week 5, which we did when we did plotting, I believe. And this week we should be doing our very first functions. Yep. So we're going to start making our own kind of contained programs today. So that's where we will start off here. Remember that you're still taking lecture notes every day, turning those into the beginning of each assignment. And also remember you also have the MATLAB shared document, which not many people have shared in. Not many people have participated in that much, so we need to make sure we get that done. But we are today in chapter 6, week 6, chapter 6, called user-defined functions. I'm on page 207 starting out today. And the very first part of this, they talk about creating M files. I think that's their first function. Creating function M files. And we've already learned how to create an M file. And so this should go pretty quickly, and then we'll move on to, well, actually they move on to making a function right away. So we're good to go. So let's go ahead and start. We're going to start by opening up an M file. You can go up here to new script or new, either one, and it'll take you to the option, your option for making a script. Or if you go to the new one, you can actually create a new function by hitting create a new function. And then it actually starts it for you. If you hit the new script one, this is what it'll give you just an empty script that just looks like an open text file like this. So it'll just give you one of these. If you hit the new function one, it'll put some text in the file. And it actually doesn't call it a .m, even though this file will be a .m file still. It opens the script file. It puts in a line of code where it uses a MATLAB saved command called function. It's a MATLAB function called function. And then it's got some square brackets with output arguments in it, and then equals untitled and then it's got parentheses, input arguments. We'll learn how to use those here in just a second. And then it tells you what to do. It says untitled summary of this function goes right here. So you're going to go ahead and put in some text here to talk about what this function does. And then at the bottom of this, it has an end. Because at the end of each function M file, you do have to end it. Because once you start function, once you put in function into MATLAB, it's expecting you to put in some code and then tell you when, and then you're supposed to tell MATLAB when this function is done doing what it does. And this is no different than the functions that are already in MATLAB. The sine function, for example, has a file like this in MATLAB that's saved into MATLAB that is a function file that tells MATLAB what to do when somebody asks for the sign of a number. And it's the same when you use any of the other functions that we have in here, like what were some of the functions we used last time? Some of the new ones. Well, we've used the pause function. It tells MATLAB what to do with that. We used the surf function. We used the contour plot function, the subplot function. You know, all these functions are just these M files that are saved in MATLAB, or these files. They're not necessarily M files, but they're files that are saved in MATLAB that MATLAB accesses when you call that function. And now you're going to make your own function that has a name that is not saved in MATLAB, but is saved in your own files. And when you call that file, MATLAB will go and look for it in your files, and it will do whatever you've told it to do inside of that program. So that's what we're supposed to do today. That's what we're supposed to learn today. So let's start off with, first of all, naming it. Let's see here. Okay. Whenever MATLAB gives you this square bracket notation here, that means that nothing needs to be put in parentheses. You're just going to put something here. You don't even need the square brackets. You can take those square brackets out. And you can just, and at this point you need to name the output of your argument. So I'm going to just call it output for now. So it's going to be function output equals. So the output of this function, whatever you're going to spit out of this function, is going to equal something. Now, right now, our function is untitled. So I'm going to actually give it a name. I'm going to call it my underscore function. Now, the naming of functions in MATLAB follows the same rules as the naming of M files in MATLAB. You cannot start them with numbers. You cannot have any spaces, dashes, slashes, colons, periods, or anything like that in them. You can use underscores, but they follow the same rules, and you shouldn't use the name of a function already used in MATLAB. So you got to be careful with that, because you don't want to have two functions, one that's saved by MATLAB, one that's saved in your workspace, that have the same name. You can really confuse yourself that way. And then after you've got the name of your function, you should have some input arguments. In other words, the user is going to now maybe give the computer some numbers to work with. You don't have to have input arguments. You can have a function that doesn't require the user to do anything. You can just say, this function is going to be called graph my favorite picture, and whenever you type graph my favorite picture into the command window, it goes to this function and it knows everything it needs to know to graph your favorite picture. But if you want this function to accept some numbers or some information and then to do something with that information, this is where you should put it, is in the parentheses after the name of your function. So we're going to start really simple, and we're going to just have a very simple input argument x. One variable, one input argument, one parameter, whatever you want to call it. So now, we're ready to go. We're ready to start programming. But what does this all mean, really? What this really means is that the result of this function, or whatever this function is going to spit out, is going to be equal to the stuff that you put into this thing we're calling my function, and all the commands that follow after this until we end this function. We've told MATLAB we're starting a function. We've told it what the output is going to look like, what it's going to be named. We've told it what the name of the function is going to be and what the input arguments. Now we're going to use those things to do some math. So here is the math that we're going to do. Let's do let's do this. So let's now down in our code here, after we've named the function and before we've ended the function, we're going to put in some calculation. And let's say that the output, so output is an actual variable that we've already told MATLAB is going to exist. So output is going to equal, in this case, a polynomial. 3 times x to the third power plus, and we're at the top of page 209, plus 5 times, this is x, we're using the dot notation here so that we can use 5 times x dot to the, so we can use a matrix if we want to. And then minus 2 times x plus 1. Plus 1. So that's going to be my output. Now I'm going to suppress that output really quick. And hold on just a second. I need to blow my nose. Allergy season has come early this year, so. Hopefully we'll get that snow they've been talking about tonight, and it'll suppress my allergy problems down a little bit. But anyway, so what we've done here so far is we've said, hey MATLAB, we're building this function. It's going to be called my function, and we're going to do some math here after this with the variable x that the user is going to put in. And whatever that x that gets put in, we're going to put it into this thing, and we're going to do this calculation, and that's going to be equal to the output of this. And MATLAB will spit this out. Now, I'm going to have to save this, but I really want to save this with the same name right here as I've got in the title of the file. So let's go up here and save, and it's going to automatically do that for me, which is nice. It's going to save it as my_function.m. The MATLAB code, the code is of .m here. And we're going to save that. Now, we're going to save it in the current folder that we're in, which is what it's going to save it in, which is good, because we really want to be able to access it. If I go up here to the current folder that I'm in, I should have myfunction.m. It's right there. If it's not there, then I will not be able to call it from the command window. So now let's go down to the command window now that I've saved this function, and let's use this function. Let's see if I can do it. My function, and I need an underscore there, and let's see what happens. My function, right? Error using my function, not enough input arguments. What does that mean? What did I forget to do? Didn't I say that this function requires something from the user? What do I need to tell MATLAB when I'm using this function? I need to tell it what x is, right? It needs to know what x is. So I need to, in my workspace over here, I have to have something that says, MATLAB, this is what x is. So the first thing I need to do is I need to say x equals something. I say x equals 4. Let's do x equals 1 to make it easy. So x equals 1. Now MATLAB has a value for x. Now I can go ahead and put in my function, and I can go ahead and do my function x. I'm telling it to use x that is already saved here, and then I can do that. And it'll tell me that my function will equal 7 when x is equal to 1. Is that true? Well, 3 times 1 plus 5 times 1 minus 2 times 1 plus 1 is equal to 7, right? 3 plus 5 minus 2 plus 1. That equals 7. I could also do it like this. I could also just say my function with 1 in it for x. That'll give me the same answer, either way. I don't have to define 1 in my workspace necessarily. I can actually just say, use my function with 1. I can also do it with 2. It'll give me the answer. But I can also do it with an array. So if I go up here to x and I change what x is, x right now is 1. But what if I change it to 1, 2, 3, 4, 5, 6, 7, and so on and so forth? So I can know what it is for all of these numbers. Oh, you still can't see up there? What's going on? Yeah, speak up if it's not on the screen. Is that okay? Oh, it just disappeared? It's like it thinks we're not in the room or something. We don't need that. It doesn't look like it's coming back on anytime real soon. I wonder if it overheats because of the air blowing on it. Like, I wonder if this air is warm. No, it's not warm air. It shouldn't overheat because of that. It's cool air. I wonder if it overheats because it's a piece of junk. Okay, so I'll just describe what I'm doing to you here. For this here. I've just, instead of having x just equal to one number, the number 1, I'm making an array of numbers from 1 to 7, a row vector, there it is. So I'm just changing what x is, and now x has got 7 numbers in it, 1 through 7, and I can actually use that array in this function. And it will give me an answer that has 7 columns. For x equals 1, this polynomial gives me 7. For x equals 2, gives me 41. Those are 2 that I've already calculated. For 3, it gives me 121. And so on all the way till 7, it gives me 1261. I can also do it for, if I open up x here, and I give x multiple rows. Oops, can't use D, whatever else. Give it multiple rows, it will do that as well. It will do it point by point, element by element. And then the answer that it returns will, of course, be a matrix of the same proportions. Okay, so very simple function, not too difficult to see. The other thing that you can do with functions like this is you don't necessarily have to use x. You don't necessarily have to plug in x. If I make another variable called y and let it equal 34, let's let it equal all of the numbers between 0 and 10. Linearly, let's do 23 numbers between 0 and 10 that are linear space, so we use linspace to create this vector. Linspace. Oh, I shouldn't use brackets, I should use parentheses for that. So I'm creating this vector here now that's y. It's 1 by 20. It's a 1 by 23 vector. Looks like this, and it's got all these linearly spaced weird numbers in it and whatever else. I could also use y in my. It doesn't have to be called x. if I want to use my function, I can plug in any vector in here at all, any number at all. It doesn't have to be called x, even though I called it x within, even though inside of the function it's called x, I can call it y out here and plug it in and it'll still do the math. Because inside the function it reassigns everything. Whatever number you put in here, it puts into this equation in place of x. Doesn't matter if it's called a different thing outside in the command window. So, excuse me. Let's take a look at another one here. Let's actually look at the example 6.1. In example 6.1, they want to convert between degrees and radians, which we're going to go ahead and do. We're going to create a function for that. So let's go ahead and start with a new function. I've got this function done and saved. I'm just going to close it, and I'm going to close this one too. And I'm going to open up here. I'm going to go up to open. I'm going to go up to new. I'm going to get a new function. And so I've got my new function here. And I'm going to go ahead and clear everything out here. And let's start again. So we got a new function. Now when I'm building functions, I like to have the command window open here so that I can use it to test things if I'm not sure how to make some code up here. Because it's much easier to test things in the command window where it will just execute it really quickly than to test it in a function where you have to actually run the function every time. So let's start with, let's go here. We're going to convert between degrees and radians. Now, one of the things when we start building functions that we need to learn is how to kind of plan out our programs. And that's something that we've talked about a little bit, but not a whole lot. So let's talk about this a little bit. Let's plan out our program here. How do we do that? Well, it requires a little bit of writing usually. Usually I just like to sketch it out on paper, but since I don't have a piece of paper here, I'll use Microsoft Word. I'm a terrible typist, as you've discovered, but we'll do this anyway. So So right now I'm going to do an outline. So this is my outline function for converting degrees to radians for angle. Okay? Simple enough. The first thing that we want to do is we want to maybe write just a summary of what we want to do, a summary of the program. So just a simple couple of sentences. This program will take an angle in degree measure and do the calculation to convert it into radian measure. After that, it will make a table of the corresponding angle measurements. Okay, good. Next thing we want to do is we want to talk about the inputs. So what is this going to expect us to put in as the user? Well, user will input, let's see, a vector of degree values and a vector of radian values. Yeah, so I guess what we're going to do is don't really want it to do that. I want it to do something slightly different than that. I want it to, we'll input a lowest degree value and a highest, no. Then we input a vector of degree values. They want converted and displayed. So however many you want converted, however many you want displayed, that's what you're going to put in. And displayed. And then we do outputs. Right? So outputs, what are the outputs going to look like? Well, the outputs are going to be a table of the inputted degree values, inputted, with the corresponding radian values. Right? Great. So there's our overview, our inputs, our outputs, and that's a good way to start when we're talking about outlining a program. It's not the end. It's not a complete thing of doing it. We could do a lot more, but we'll save that for later in the class when we have more complex programs. But this is something you should write down before you're doing a problem. Just kind of so you can map it out in your head a little bit and get used to outlining programs, because we're going to have to use that skill later. So, moving on, we've got that done. Now, let's see if we can't figure out how to do this. So let's start up here with naming our function. So we start off by telling MATLAB we're going to make a function, so we call it function. And the output arguments, we have to have some kind of name for our output arguments. Let's call it table underscore of degrees underscore versus underscore radians. Why not? So that's great. The function will, the output will be called table of degrees versus radians. And sure, why not? And this is going to equal the name of our function. So this part is our name of our function. We'll call it, why not? We'll call it radian degrees underscore radians. Not slash, can't use slash, underscore radians. Degrees radians, that's fine. And our input arguments, we can call that whatever we want. We just want them to input a vector. So we can call it whatever we want. Call it Z, call it Q, I don't care. I'll call it S. Call it whatever you want. Whatever you use right there, though, is the variable that has to be down here. So let's write some things in here really quick. First of all, our title. I'm just going to copy this title of our function, which is degrees underscore radians. Copy that. I'm going to put it right here. Paste. So degrees versus radius, I'm going to put a summary of this function here, which we already wrote. Degrees versus radius is a function that converts angle measurements in degrees into radian. Right? So pretty simple. I can do a detailed explanation here. For example, I might say the input is a vector of degree measurements, and the output is a table of the input and the corresponding radian measurements. Sure, why not? Apparently, oh, there's my end. Okay, so now in this spot here, which I like to put a couple of spaces after this. I also like to put one in here just because I don't like things like that. But anyway, I like to put a couple spaces in here to offset my actual code so that it's not all crowded up there with all the explanations. So let's go ahead and start this off. Now we're to the point where we're going to be writing code. It turns out that the formula for doing this is pretty simple, not very difficult to do at all. And so it looks like this. Radians equals so if I have 30 degrees, for example, I take 30, I'm going to multiply it by 360 divided by pi is what you want to multiply by. So that ends up being the same as 180 divided by, no, 360 divided by 2 pi, which is the same as 180 divided by pi. So if we just do that, that gives us the correct number of radians. Turns out that's not correct. Why is that wrong? Nope, it's the other way around. Sorry. It's 2 pi divided by 360. That's what it is. So it ends up being pi divided by 180. There we go. So there is the radians for 30 degrees. 30 degrees gets you about a half of a radian. And let's see if that's correct. That sounds right. 30 degrees, about a half a radian. And yeah, okay. So this is, this works, is essentially what I'm getting at. This is the equation that we need to use, but in place of 30, we need to put in a variable, and that is what we're going to put up here. We'll just copy this, throw it up here. Now we need to change some things, however, because right now we have our output is table of degrees versus radians, and our degrees radians is using a variable called s, and so what we need to plug into this equation is s. S times pi over 180 equals radians. And that's fine. That'll work for us. We're going to suppress that output so it doesn't print to the screen. And then we're going to go ahead and use and do our table. So how are we going to do our table? So let's start down here with a vector. Let's use a vector for degrees. We'll call it d equals, and we're going to go from 0. We'll make a vector of numbers from 0 to 180, and we'll do it in steps of 15 degrees. So from 0 to 180 in steps of 15 degrees, and those are going to be, this is going to be our table of degrees. It's going to look like this: 0, 15, 30, 45, 60, 75, so on and so forth, all the way up to 180. So it's got 12 numbers in it, and now we need to go ahead and do some calculations. Well, we've seen the calculation. The calculation looks like this: radians equals our degrees, which in this case is going to be d for degrees, times pi over 180. And so here's our table of radians. Right? So now we've got two things that we've done here. So in the first case, they plug in the degrees, we plug in the degrees here, and we create this table. We've already done all that. We know that math works. Now how do we actually make the table? Well, the table of degrees versus radians is the thing that we want to name this. We'll just call it table down here for now. So our table is going to equal a vector of these two things. or on a matrix of these two things. And we want to make this with two columns. So we'll take the first thing, which was the D, and we'll invert it into a column. And then we'll take the second thing, which is we called radians. We'll invert that into a column, and we'll see if it gives us what we want. And that's exactly what we want. We want this table to look like that. So that's our next command that's going to work. We take that command, copy it, put it into our function, paste it. We might want to make a comment here. This builds our table. We're going to want to rename this to table of degrees and radians so that the function outputs it. Copy this and rename this table of degrees and radians so the function knows that that's the thing that it spits out. And then instead of using D here, we're going to use S because that's the thing that we use just randomly. And maybe we put up here, we put a little comment line up here that says this calculates radians from D. So we've got some comment lines in here. We've got our 2 lines of code. We've got everything using the correct variables. We're using table of degrees for our output. That's what we said it was going to be. The output is going to be tables of degrees versus radians. Our input is S. The variable that we're using throughout here is S. And we've also introduced a new variable called radians. This variable here will only stay inside of this function. So we save this thing. We're calling it degrees underscore radians. It accepts one thing. Let's go down here to our window. I'm going to clear everything in the window. I'm going to also clear all the workspace so we don't have any things floating around in there. And now we're going to use degrees underscore radians function. Degrees underscore radians as a function. Of course, it is expecting an input argument. Once again, we have to tell it what we're using. So let's create a thing called degrees. So this is going to be degrees, and we're going to have the numbers. Let's go from 0 to 90 in steps of 5 degrees. So 0, 5, 90. Okay. So there's our degrees from 0 to 90. There's 19 of those. And if we go up here and we do degrees, radians, and we put parentheses after it and put in our vector that we call degrees, it gives us a nice table here called table of degrees versus radians. It also punches it out as the answer. Unfortunately, we can learn how to suppress that if we want to. But if we wanted to suppress the table of degrees versus radians, we would just put a semicolon there, and then we would only get one thing out of the function. We have to save that up here. So we go up here and we save that. And then we come back down here and we call degrees versus radians again, and it only gives us the answer right there out of the function. And we'll learn more about how we can make that a little cleaner as we move along. But here it's done the whole table. So for 0 degrees, it's 0 radians. For 5 degrees, it's 0.08 radians. For 10 degrees, it's 0.17 radians. And so on and so forth. And we just made this table of degrees versus radians. You can do the same thing with inches versus centimeters. You can do things in miles and kilometers. I mean, there's a lot of different things you could do here to make these tables. Let's do another one. Let's do example 6.2, where we're not only going to do a calculation, but we're also going to make a plot. So let's go up here and close out this function. Degrees versus radians. Let's go up to new. Let's open a new function. Go down here to this window where I like to clear everything when I'm working with functions so that I don't have things messing me up. I like to do that anyway. But. So let's create a new function. What's this new function all about in 6.2? Let's go back to Word and let's map this out a little bit. So, in this new one, we're doing ASTM grain size. So here they say we're not used to thinking of metals as crystals, but they are. So crystals, metals are in their metallic form. It's very obvious that they're crystals when you look at them very up close. And the grain size of that crystal is essentially the size of individual crystals on average. Take a look at that because that's kind of interesting. Let's look at electron. Some images of metals. So this is what it looks like when you look at metals close up. You get this crystalline structure. Some of them it's more obvious that it's crystalline than others. For example, these are obviously more crystalline than some of these, but they're definitely crystalline the closer you look at them. And some of them, it's very obviously so, they have these very geometric structures to them that suggest that crystalline structure very, very much. But anyway, the average size of one of these crystalline units is what they're talking about with grain size here. And so we're going to put in a function that can actually let's see, calculates the number of, it calculates the grain size if you have the number of grains per square inch at 100 times magnification. So the equation is fairly complex, but we don't need to actually understand the equation to just enter it in, so we're not going to worry about where it comes from. We're just going to enter it in. But the bottom line is, what are we doing? So what are we doing? This function will calculate the grain size, and I'm going to go ahead and put it in what the grain size is in this equation, little n, from the number of grains per square inch at 100 times magnification. The number of grains per square inch is going to be capital N. So we have two n's, and this is a good thing to keep them separate right from the start. And the equation that we'll use, the equation is given. That's good enough. User, so let's do input. Input will be user will provide n. Output little n, and a plot of n little n as a function of n, of big N. So little n will be on the y-axis, big N will be on the x-axis. So that is what we're going, that's kind of the outline of what we're doing here. Let's go ahead and create a function. So let's call this function, we'll follow along with the book this time, I kind of deviated last time. They're going to go ahead and just call this output, and that's fine. I'm going to call this part output. And that's going to equal, they're going to title this function grain size. That's fine, that's a good one too. Grain underscore size. That's fine too. And then the input, they're going to go ahead and call it big N, just like we did in our little summary, right? We can insert the summary here. I actually saved it this time, so I can actually go back to Microsoft Word somewhere. Where did I put it? There it is. So I can actually just copy this now this time. It's kind of convenient. Put it in right here. Whoa! Now when this happens and you paste some stuff in and it doesn't make all of it comment lines, you can highlight it and you can comment it all by pushing a button up here or right-clicking on it. If you right-click on it, then you can come down here to comment it. You can make it all comment lines. So it's all comment lines now. And I'm going to remove spaces, and I'm going to remove some of these lines that are not necessary for this part of it. Delete that, delete. Don't need all of this. Excuse me. So n and plot of n as a function of n will be outputted. And there's my detailed explanation. Okay, so I've got all that in there now. That's my summary of this function. I give myself some space to write my function. Now I'm going to input the equation, right? So the equation is the one that they give in the book, of course, and it looks like this. Little n equals big N, no, equals the log of big N, and there's going to be parentheses around this. The log of big N plus the log of 2, and then close parentheses, and then we're going to divide by the log of 2. So there's our equation that we've got to put in here. And if you put in different numbers, it will give you different outputs every time. You can put them in a whole array of numbers. But the problem with using logarithms is that when we use log in MATLAB, it means the log base E. It means the natural log. So we actually need to tell it which log. So we need to use log 10. That's a different function in MATLAB. That means the log base 10, because in the problem, it was the log base 10 that they used. Turns out it will work either way in this particular case, but that will not always be the case. So we go ahead and put log base 10 in, and that's great. And then that is our little n, right there. However, in this problem, we actually want that to be our output. So we call it the output. That's output up there. So now that's the thing that we're going to spit out. That's one of the things we're going to spit out. The other thing that we're going to do is we're going to create a chart. So what is we're going to create a graph, a plot of this. Excuse me. And so we can use the output as part of our plot, and we can use the input from the user as part of our plot, n and output. So we can just do here plot big N, comma little n. Remember, x is first, y is second, and we can do that. However, we also would like to be very professional, so we'd like to give this plot a title, and we will call it ASTM grain size. Remember that you have to put quote marks in there to make that work. And then we also want to label the axes. So we'll do an X label. And the X label, we'll call it number of grains per square inch at 100 times magnification. Then we'll do a Y label. we'll just we'll do a Y label. And the Y label will look like ASTM grain size. And maybe we'll turn on the grid just to make it easier to read. Turn on the grid. And then we can end it. Now the end can come. And if we want to put in some comment lines, we could put in some comment lines. We could say, for example, put some space in here between this one and say this is the calculation. Say something like this is the plot, so on and so forth. Don't need much more than that. It's pretty self-explanatory. Make sure it's all good. Make sure there's an end on it. That's great. Next thing we got to do is we got to save the file. Remember that this is the title, grain_size. I'm going to go ahead and copy that because that's what I need to save it as. But it turns out MATLAB is very nice. I keep forgetting this. MATLAB didn't used to be this nice. When I go to save, if I've opened this as a new function, it'll automatically save it with the correct title. MATLAB is becoming so easy to use, it's just ridiculous. So I've just saved this as grain size. I go down here and I type in grain_size. It's going to expect some numbers that I'm going to input. So I'm going to input a group of numbers. I'll make a matrix, or I'll just put in a group of numbers. I'll go ahead and make a vector here of just some random numbers that maybe I was counting when I did my research, and these are the numbers that I got, and whatever else. I don't know why I put commas in there, I don't usually. And so I go ahead and hit that, and we got a problem. Undefined function or variable little n. So where is little n? It's inside of here, inside of our thing. We put plot little n, but we don't want to plot little n, we want to plot the output, because that was our little n. So we made a mistake in our function. We go back, we fix our function, we save it, and it actually tells you where your error is. It tells you it's in grain size, line 9. So that's where I was able to look really quickly. I looked in line 9 of grain size, there's my error. I fixed it, I saved it, I go back to here, I run the function, and there it is. Now this maybe is not the best type of plot for grain size. This line plot where all the points are connected. Maybe I ought to done points instead of lines, instead of connectors or something. So I could fix that. Let's go back and fix that. We go into here, and let's first let's go to our command window and let's remember all the stuff that we can do with plot. So plot is the function. I'm going to look for help on the function plot. And what I want to look at is maybe I'll start with different kinds of plots. There's a scatter plot. I think that might be a good one. Let's look at that. Scatter plot. So a scatter plot displayed color circles at the locations specified. And that's what I want. So maybe I want to change this plot instead of plot to scatter, because it'll just give me a bunch of points. Scatter. Let's try that. We have to save it again. Right? And then we go back to our command window and we run that command again for our grain size function. And there we go. That makes a little more sense. We have now just these, and it actually puts them in order of size. So we start off with the smaller ones here, and then it goes bigger. And that's kind of nice. It cleans it up for us a little bit. So, let's see here. Anything else we want to touch on with this particular one? I don't think so. All right, good. This is, let's see if this is cool. Let's actually look at our own function. Help, and let's look at, let's actually look at help. What's my function called? Grain size. Grain underscore size. Let's see if it tells us anything about this. Look at that. If I've entered in my own function, and if I ask for help, it'll actually bring up the little summary that I wrote. And that's kind of nice. It actually knows how to find the information about your function. What it does is it looks for the first group of comment lines after you've named your function. So those are the ones that you put in here. So it's really a good idea to make good descriptions of your functions so that you can figure out what they do really quickly. When you get to the point of doing the final project, you'll have multiple functions, maybe even as many as a dozen or 20 functions that are within a single program that you made all those functions. And maybe you don't remember which one of them does exactly. So it's a really quick way to figure out what something does, even if it's a function you wrote. Okay, now let's take the next step. Let's have multiple inputs. It's not all that hard, actually. Time is it just after 1? Trying to remember. We do multiple inputs. We do 3 inputs. Functions with no inputs. Local variables, which we already did on accident. And then toolboxes of functions. And functions. Yeah, those are weird. And then subfunctions, okay. So let's do another one really quick. Let's do a function with multiple inputs. Now, you might say, this function you just did accepts multiple numbers as an input, but this function only uses whatever you put in as one variable. So it might be a whole array of numbers, but it plugs that whole array in at once. What if I want something to plug in an array, plug in 2 different numbers in 2 different places inside of my function? So let's take a look at how that might be done. Let's create a new function. Again, we have function, we have our output arguments. We'll go ahead and use output here again, just output. That's not uncommon for people to just call it output. Sometimes people give it specific values so that it comes out and they can use it as variables in the workspace. In fact, let's go ahead and do that really quick just so we can see how that might be used. Let's call this the product. I don't know if product can be used here. Let's find help for product. So MATLAB doesn't know what that means, so we can use it. What's the other one that you can do? You can use whose. Is it? That's not it. Anyway, it doesn't matter. So we can use product is going to equal this function that we call we'll call this. Let's see, what are they calling it here? They're actually calling it G. Okay, we'll just call it G. They've just given it the name little g. That's fine. That works. But they're going to have 2 arguments that they're going to put in. So you have to have 2 variable names. X comma y, for example, would work. Or a comma b would work. Whatever you choose to use up here still are the variables that you have to use below in your function. So you have to use those ones down here when you're doing your math. That way MATLAB knows that the numbers that get plugged in here get used down here. So I'll use a and b. They use x and y. It doesn't really matter. And let's go into this this summary here, and let's say this takes in 2 separate values, or 2 separate. We'll just call them 2 separate. Yeah, we'll call them values, and multiplies them together. Now, this works term by term with arrays or matrices. That means that we have to do our math down here as if they were plugging in arrays and matrices, and make sure we use the dot times, right? And so our output, the answer, the thing that this function is going to push out at the end, or is going to spit out at the end, is going to equal a times b, but it's not just going to be a times b, it's going to be a dot times b. So, whoops. Dot times b. It'll be a, not just a times b, but a dot times b, so that if there are two arrays, it will do it element by element and still give an answer, instead of trying to do some crazy cross product or dot product that will give us strange results if we don't know what we're looking at. So there's a very simple function. And it's called G. What else do we need to do here? That's about it. So let's save it. Saves it as G. Fine. Good enough. We go down here, we put in G. And we want to know G of two different numbers. So it's going to be 3 and 2. Well, I made a mistake up here, but let's find out that we made this mistake here in a second. Notice that I called this thing product, and I called this output. When I ran my function, nothing got spit out. Because I didn't name my output, I named it product. So up here I need to name this product. Because my output is actually called product. So if I call this product and I save it again, and then I run G, 3, 2, then it's going to give me an answer of 6. Otherwise, this function doesn't do anything. It just created a new variable called output, multiplied A and B together to give me that, and it was good. So let's change this. Let's give it something more complex. Let's give it x equals 4, 5, 6, and oops. X equals 4, 5, 6, 7, 8, 9, 8, 9, 1, 2, 3, 3. So there's my X. Let's do a Y that equals Y that equals 1, 1, 1, 2, 2, 2, 3, 3, 3. So there's my Y. And now let's go ahead and do G of X and Y. Right? And there it is. Multiplied the first row by 1, the second row by 2, the third row by 3. Right? Okay. So, excuse me. You can also do something like this, where I multiply x by y prime. So I'm inverting y. I'm going to turn it on, make its rows columns and its columns rows, and then multiply it. It'll do that as well. So it multiplied the first column by 1, the first column by, second column by 2, third column by 3, so on and so forth. So there you go. You've got now two variables that, or two inputs into your function, and you use them both. Notice that the function has both of these, this A and this B in here. You don't necessarily have to call it A and B out here, though. So let's do a more complicated one. Open up a new function. This one is going to be how grain size affects metal strength. So we're going back to grain size, okay. So it says here metals, this is on page 217, how metals composed of small crystals are stronger than metals composed of fewer large crystals. The metal yield strength, or the amount of stress at which the metal starts to deform or bend permanently, is related to the average grain diameter by the Hall-Pecht equation. They've given us the Hall-Pecht equation here. And it's this crazy equation with sigmas and k's and d's to the -1/2 power and all this stuff. And so we need to figure out what we're going to do here. Everything in this equation is something we're going to have to plug in. This one's going to calculate the yield strength. So we're calculating yield strength instead of yield strength. And yield strength is, in this equation, called sigma. So sigma looks like this, in case you're wondering. I'll show it to you really quick here. We will go to insert. We'll insert a symbol. And if we go down the symbols here to the Greek letters, here are the Greek letters. Sigma is this guy right here. Why won't it let me insert that? Huh. Let's try that again. Insert a symbol. And the symbol I want to insert is this one, small letter sigma. I didn't do it. Why? Oh, I think I have to drag it in. There we go. That's right. Okay, so there's my sigma. I'm going to copy that because I'm going to need it again. And it's going to calculate it from 3 different things. It's going to be from the sigma naught, where sigma naught is a number from, and it's going to calculate it also from K. Let's see. So it's going to be from 2 values. Let's see. I don't want this. This is kind of lame. Okay, so anyway, from we'll just paste it in here. Sigma sub 0, so I'll do a little sub thing here, wherever that is. How do I do it? Here we go. Sigma sub 0. K and D, I guess. It's all bold face, I don't know why. Get rid of the bold face. Okay, so anyway, there's our stuff. And we could explain what K and D are. It's not important to us right now, but K is essentially a constant. Sigma is a pressure. So it's just information. D is a distance. D is a size, essentially. So we don't necessarily need to know what those are, but we do need the equation, and it is given. We'll show that one in a second. The user input will be the 3 values here. So the user input will be sigma naught, K, and D. We'll just go ahead and, oops. There we go. Okay. So we want to copy that. We want to paste this, sigma K and D. The output will be a plot. This will be a plot of sigma versus sigma naught. So we've got it all mapped out here in our little thing here, sigma versus sigma naught. Okay, we got it. No problem. So back to our function. Let's copy this whole thing so that we have it in our, so we can paste it in our function. Go ahead and paste that description in our function really quick here. Paste. Remember that we have this thing that we want to comment all of this. We'll get rid of some of the spaces in here. We don't need. Okay, so there's my description of my function. What are we going to call this function? We're calling this, I don't know what we're calling this, probably strength or yield strength. They're calling it Hall pect. We'll call it yield strength. If you capitalize a letter in your function title here, you have to capitalize it everywhere. So I'm going to go ahead and do that really quick just to show that. So I'm calling this yield strength. My input arguments are going to be 3 arguments. Now I'm not going to necessarily use sigma because that's a pain in the sigma. Let's use S for sigma. So S0 would just be S0. And then for our K, we can just use capital K, and for our D, we can just use little d. And our output will just be our output. Now, in this case, we're not necessarily going to use the output at all. We're not going to actually type any numbers to the screen. We're just going to create a graph. So that's fine. We don't have to use output in our code anywhere. But we do need to have it here. It needs to be put in here so that it satisfies the requirement of MATLAB. So let's go ahead and start with our equation. And we'll call this the Hall pect equation. We'll go ahead and put some comment lines in here. Hall slash pect. Hall pect equation, we call it, so we remember whose equation this is, in case they lose it. And we'll say we could go ahead and start with an equation like this that says output. So the output would equal whatever the equation is. So output would be our sigma, in other words. And we could use our equation. The equation that's given on the book on page 217 says that sigma naught, so that's our S0, plus, you add to that, there we go, big K times D, little d, but we raise little d to the -1/2 power, so -1/2 up here. And that would be fine. We could do that as an output. The problem, there's a couple of problems with this. First of all, we need to remember that we're using we can use a matrix for this, so we can plug in multiple numbers for d. So we want to have a d dot raised to the power, and that's good. That'll be better for us. And if we run this function, it's going to give us numbers. It's going to spit some numbers out to the screen. So let's go ahead and run this function as it is right now. Let's save it for yield strength. Save it right here. And that's great. There's one more thing I want to put in this function though, and that is I want to clear my workspace and I want to clear the command window inside of the function so that when I start this function, it just erases everything in my command window and erases my workspace so that it's clean out. You don't always want to do that. Maybe you never want to do that, but sometimes you can do that. There's sometimes a reason for clearing everything out before you start using a function so that it doesn't do things. You could go ahead and put that in there if you want to. Not necessary, and in some cases not recommended, but it's just something you can do and it will execute those commands. So let's just wait for that for now. Let's just have our inputs and We've got our equation good to go here. We've saved everything. So let's go ahead and down here and let's use it. So this is called yield strength. And I have the capital Y and the capital S. If I don't do that, it won't know what I'm talking about. Because over here, it's called yield strength with capital Y, capital S. You have to spell it right. It has to have the right capitals and everything else. It's expecting 3 arguments. According to the book, S0 is, sigma 0 is 12,000, so I put in 12,000. And then a comma with my capital K is 9,600, it turns out. And then for their D, they're going to use all the numbers between 0 and 10. So I'll just put in this little vector of numbers from, not from 0, but from 0.1 to 10 millimeters. And they do that in steps of, let's see, 0 to, they do that in steps of 0.1 millimeters. So they're doing a lot of these things. So we're going to do 0.1, 0.1, and they're going to go all the way up to 10 millimeters. 10. So that's a pretty big array. Like 100 numbers or something like that. So those are the numbers I'm going to plug into this. Let's see what it gives me. It gives me this 100 1 by 100 matrix of all the calculations that it did, and it prints it out to the screen because I told it to. I said output is going to equal this. Now if I go back up here and I name this something else, let's name this S, for example. And let's save that, and let's run it again. Let's go back here and run yield strength with those same numbers, and I hit return. It doesn't do anything. It doesn't print anything to the screen because I didn't tell it to output S. I didn't tell it to do anything with S. So that's actually a better thing to do if I want to put a graph out and no numbers. So now I go back up to my function and I'm going to make my graph using S for the graph. So let's plot. We want to plot S versus D, I believe. So we want to do D, comma, S. And let's see what this gives us. So let's save it and let's run it. Go back down here to yield strength, run it, and it gives me a plot. But notice on the screen there's nothing printed to the command window. Just prints out the plot. And you could put a title on that plot and label the axes and do all that stuff just like we did before in the function file. And then you would be good to go. Okay. Okay, here's another function. Let's see here. Should we take a break? It's 1:30. You can either take a break or just keep pushing through. I think I'm going to take a break, go get a drink. So we'll take a break of 5 or 6 minutes, and we'll come back here at about 1:40. And we'll come back and we'll talk about functions that have no input argument at all, and some other types of functions we can create, and finish up this chapter and move you on your way. Now you should remember this before I forget to point this out. In the homework, this particular assignment's going to be, and assignments after this are going to be different than the ones you've seen so far. Because instead of having one file with a whole bunch of work in it, every question just about is going to have its own M file because you're going to be submitting functions. So question number 2 is going to be a function M file, just one file. And all I'm going to do is download it and run it and see what happens. And question 3 is just an M file. So question 4 is just an M file, and so on and so forth. So you have individual questions, and each one of these is going to have its own M file that you're going to have to input into here. So anyway, that's what you got to do for the homework this week. I'll take 5 minutes. I'll be back, and then we'll start. All right, we're back for another round of writing functions. So functions with no input. and maybe even with no output, or both. Let's see here. Let's do a new function here. You can open multiple functions at a time, and often that's helpful if you have a lot of functions. It'll just give you a lot of tabs up here. I don't like to do it unless I need to do it, unless I'm working on multiple functions at one time that are all related to each other. So I just try to close them when I can. So I'm going to just open up a new function here, and I'm going to have no output at all. And I'm just going to leave this blank between the square brackets here. And if I do that, then it will not have any output at all, no matter what you put in. And I'm going to call this new function the star function. This should be in your homework. Should have had something like this. And I'm actually going to have no input as well. This function is going to have no input, no output. It's just going to be a function that does something that I want it to do. I want it to create a star. So I'm going to have these angles from pi over 2 to in steps of, what are the steps of 0.8 pi, 0.8 times pi, all the way to pi, all the way to 4.8 pi. So that's my theta. Those are my theta values, pi over 2, 0.8 pi, and to 4.8 pi. That sounds right. And then I'm going to create a function of r of 1s. Create not a function, but an array of 1s. R equals 1s from 1 to 6. So I want this one to be 1 comma 6. One row by 6 columns. And then I want to make a polar plot of theta and r. Simple enough. Then I end it. I can write up here, this thing's going to make a star or whatever else. I'll leave it at that for now, just for time's sake. And this is going to be saved as star, and I go down here, and I type in star. Boom. And it makes a star. The only thing it does is create a graph. It doesn't put any outputs to the command screen. It just makes a star. Plain and simple. There are actually a lot of functions like that. For example, if you use the function clock in MATLAB, it'll actually tell you the clock's value on the computer at that moment. So the clock's value is not exactly obvious that it's a clock, that it's keeping track of time, but it is. It's an array of 6 numbers that keeps track of things. So, but that can be useful in many ways. Pi is, of course, if you just type in pi, it returns the number 3.1416. That is a built-in one like this. There is another one called tick and talk in MATLAB. So if I write tick, it starts a timer. It actually reads the time on the clock, and it stores it in MATLAB. Then if I write talk, it does it again, and it takes the difference in time. So that was 5 seconds in between those. If I do tick, and then I do talk immediately, it gives me less time, of course. And that's a very important thing. That's a very important set of functions that you can use in your programming. Sometimes when you're doing a program, it's important to know how long it takes something to happen. So you put a tick before the commands you want to measure the time for, and a talk after those commands, and it'll immediately tell you how long it took those commands to run. So if I do that here in my star function, and I put a tick before this and a talk after this, it will tell me how long it took to run that function. So let's go ahead and save it, and let's run it. You can actually run a function if your cursor is inside of the function. You can run the function by hitting run. It'll do that, and it took an elapsed time of 0.100045 seconds. So about a tenth of a second to do that computation and make that graph. The more stuff you put in between that tick and the talk, of course, the more time it will take. Okay. Oh, here's a nice little thing here for if you want to know how many input arguments are in a particular function that you plug in. So if I want to know how many things I need to provide star, how many inputs I need to provide star with, it'll tell me. It says, so use this, oops, sorry. You have to put quotes around the name of your function. It tells me you don't need any inputs for that function. However, if I go to yield strength, so if I do nargin, so this is number arguments in, is what nargin stands for. So if I do nargin of yield strength, like that, hit enter. It tells me it's 3 arguments, just like we said, right? Same thing, nargin for product. We made that function, it's still saved. Product, I think I used a lowercase p for that. Nope. I apparently used capital P for that. Maybe I didn't save that one. Oh, we called that one G. That function was called G, not product. Little g. It's 2. It requires 2 things to multiply together for that project, that one to work. So just a nice little thing that you can use there. Also, you can ask how many are out, number of arguments out, called narg out. Number of arguments out. And you can put in whatever you want. So for G, 1 argument out. And we haven't done one with multiple arguments out yet. We'll do that one. We'll do that next year, I think. Not quite. Let's see, did we do one with multiple outputs? We didn't. Okay, so if you're going to do multiple outputs in a function, you just need to name multiple outputs up here. So maybe output 1, output 2, output 3 up here within brackets. So in these function brackets here, you might, if you're going to have multiple outputs, you just make an array of multiple outputs. It could be out 1, comma, out 2. You can actually use spaces as well. Out 3, and those would be your multiple outputs. And then down here in your code, you would just have multiple outputs that you would print to the screen. So you could use those outputs down here to assign numbers to them or whatever. And you can do those in many different ways. We'll see an example of that here later, I think. We'll try to use it later. Anyway, okay, so let's do another thing here. Let's actually do I think we could do a multiple output here with this function. Let's call them output 1, output 2, output 3, and we're going to use the star function still. And now I'm going to actually make a star that has multiple, let's see if we can make a star with multiple sides, with more than 5 or less than 5 sides to it. So this is going to be, we're going to have an input here. And we're going to change this theta to be pi over 2. It'll start at pi over 2 still. And it'll go, let's see, how do we do that? We'll take 4.8 and we'll divide that. So to make a 5-pointed star, they divided 4.8 by 6. So we're going to divide this by n plus 1 because they made a 5-sided star. We'll divide it by n plus 1. You don't necessarily have to remember why or know why this is being done. And that's going to be our spacing, I think, I hope. And we'll make our 1s from 1 to n. Again, this is not something you need to know why this is working. But we'll go ahead and take the tick-tock out of this. And let's see if this works. So we'll save that. And we'll run it by typing star. And we'll do a 5 in there and see what happens. Theta rho must be the same size. I must have done something wrong. 4.8 divided by n plus 1. That would have given me 0.8. Oh, this needs to be n plus 1, not n. So this needs to be n plus 1 because it needs to go to 6. So let's save that and let's run it again. So let's see if it works with a 5-sided star. It works with a 5-sided star. Now let's see if it works with a 6-sided star. Let's try it, star 6. Maybe it will, maybe it won't. Oh, it doesn't quite work with a 6-sided star. Maybe it'll work with a 7-sided star. I'm just dreaming at this point. I'm not sure what it's going to work with because I was making it up. So it makes some kind of weird shape, but let's not really worry about it yet. Let's not worry about exactly how the geometry goes. We're making different things every number that we point in here. And that's an input that changes things, and that's fine. But let's talk about outputs here. In fact, let's go back to where we were. Let's not even worry about the input. Let's just change this back to where it was. 4.8 goes back to 0.8, 0.8, and this goes back to 6. And we take out the n. There'll be no input, and that's fine. But let's do some more outputs, though. Let's do an output right up here. And let's say that out 1 let's output some text to the screen. When you want to output text to the screen, you just put it in quotes. And we're going to say twinkle, twinkle, twinkle. There we go. Right? Twinkle, twinkle. That's output 1. And then after that'll come before we plot anything. Then afterwards we'll do out 2 will be equal to little star. Right? And then I'm going to put a pause here for a little bit. I'll pause for 3 seconds maybe. If I pause for 3 seconds and then I put in output 3 equals How I wonder what you are. Sure, why not? Then we end the program, we save the program, and run the program. So let's go ahead and run it. We don't need an input argument now. This is just back to the normal one here. And it does twinkle, twinkle, little star, and then the output 3, how I wonder what you are. Right? Now it did it, how many times did it do it? Out 2, out 3. And then it did the answers as well, because I didn't. Remember that if you don't suppress your outputs up here, it prints them twice. So it actually printed them twice. So we'll suppress those really quick. Down here. Then we'll run it again. We'll save it and run it. Still did it. I thought it didn't. Oh, that's the old one. So here's the new one. Twinkle, twinkle. Here's the new one. Twinkle, twinkle, little star. What happened? Why didn't it continue? Should have outputted all 3 of them, but it didn't. Let's see. Apparently it only outputs the first one, and it suppressed the second 2, even though it outputted the first one as the answer. So that's okay, I guess. But you can either choose to do it or not choose to do it. We'll just choose to print these, and then we'll print them. But anyway, you can have multiple outputs to the screen and multiple outputs to here as well, to the workspace. So let's go ahead and try it again. Star. So output 2 is now printed out here as well. Output 3 is printed and the first one printed. So anyway, you can have multiple outputs is the point. Still does that answer thing, which is, I just think, kind of goofy. Answer to the function. So, let's see, what else can we do that's, oh, the next thing we have to do is variables. Now we already talked about this, that within the function you can use variables that are not used outside of the function, and it's shown right here. Right here we created the variable theta and the variable r, and we use them right here, theta and r, but they never show up over here in our workspace. In other words, MATLAB doesn't know that these variables exist. Only the function knows that they exist. They're used in the function to do what the function needs to do, but they're not used outside of the function. Those are called local variables. They're only local to the function. We don't care we don't care to use them outside the function. Matter of fact, we maybe never want to use them outside of the function. But there is such a thing as what is called a global variable that can be used both outside and inside the function. And global variables have to be, if you're going to declare a global variable inside of your function, then you have to actually name it such. So let's say that you wanted this little r in here to be global. Then you need to actually call it a global variable. You need to use the function global, and then you need to say r is going to be global. So global r. And it will highlight it in blue inside of your function. And when you run this function, now we save this function, and then we run this function, that global variable r will be usable everywhere in MATLAB. You'll be able to assign it from everywhere and use it everywhere. If I go down here, I should be able to see that variable now. No, let's see, that's not right. Oh, first you have to actually give it a value out here. So if you say global r, then the function will look for the variable over here in the workspace. Over here, I've already defined the variable, and that's the danger of using global variables. Since I've defined the variable in here, then it already has a value for it, so I've redefined it. If I want to use a global variable, I want to define the global variable out here in the workspace and make it here. And then this function knows that the variable is over here, and you can still use it. Even though I haven't told this function what R is, since R is already done out here, I can still run this function and it'll still work, because it knows to look for R out in the global variable. So all these variables out here are essentially considered global variables, but you have to tell your function to look for them if you're looking for a variable out here in the workspace. I generally do not use global variables very often, just because it can be really messy, but some people use them quite a bit. They can be efficient. It can be efficient to use global variables, but it can be messy also. Okay. We're getting there. We're getting there. This is a long one today. Another way that you can get to your files, other than just clicking them clicking on them over here in your folder, is you can actually use the function type and put in the name of a function. For example, type G. Except I have to use G in quotes. I always forget that. Single quotes. Then it'll show you the text that's in G here. It won't necessarily allow you to edit it. I don't think you can edit this at all. It doesn't change anything. But you can actually bring up what the code is without actually having to open up the window, open this thing up here. If you use this to look for one that's a MATLAB command, it will do that for you too. So this is a function in MATLAB, and it's a little bit more complex than our little G function, but it will do that for you. Next thing that we want to learn really quick, not a difficult thing, but it's one of those things we want to learn, is how to create a toolbox of functions. Sometimes you're going to build a whole bunch of functions that are all related to each other for some reason. Maybe they're all for the same project, or maybe they all do very similar things. Maybe they all work with circuits, maybe they all work with mechanics. Maybe they're all about measuring something with mountains or whatever. And you can create toolboxes, which are essentially just folders filled with these particular functions. So the way that we do this is we create a path to these functions. And let's see here. We do this by typing path tool. So the path tool shows you essentially all the files that you have to go through to get into something. So you start on the right and go to the left, essentially. Let's close this really quick. There's also a add path is what it's called. Help add path. So add path. Input, add path, input. Well, you have to have a directory name in there, so you don't have that right now. Okay, so let's go back to path tool. If we go to path tool, we have this option to add a folder in here, or to add a folder with subfolders, either way. And what that's going to do is it's going to allow you to create a new folder to put functions in. And that gives, and it also gives you an object, gives you a option to add a folder with subfolders in. This is not something we will use a lot in this class, but it is something you might use if you get really into this, where you have so many functions that you have to keep track of. So we won't go into it. We're not going to go into it in much more detail, other than it's just a way of organizing your functions. If it interests you because you're interested in programming, you'll definitely have opportunities to learn about it. But there's another way of doing it as well. The other way is to come over here to your folders and start adding folders. So you can open up folders, and you can right-click on folders, and you can go back to folders, and you can do all kinds of things. You can create new folders and new files, and add to path. You can do all kinds of things. So you can do the same things over here like you would in Windows. A lot of people still like to have these tools in the command window, but also they're useful when you have to create paths within functions. Because in huge programs where you're taking huge amounts of data and trying to organize it, you don't want to organize your data by hand. You'd prefer to have the computer do it. So create a program that tells the computer to open a new path and to open a new folder and to put data in that folder or put a function in that folder or whatever else. So this actually tells a computer how to navigate a computer, is what it is. So they're just functions for doing that. They mention them because it is useful, but not necessarily to us right now. This next part is going to be tricky for me, because this is something that I've only had a little bit of experience in. I only started doing this last year a little bit. And it's called anonymous functions and function handles. So we've already built functions. We've built several functions already. And we did it by building the function within a M file, and then saving that M file with that name of that function, and then calling that file every time we wanted to use that function. And that file had to be within this, the current folder. We had to have all the correct inputs and everything else. However, with smaller, simpler functions like we've been doing, sometimes there's an easier way to create the function within our program. So we create the function without creating an extra M file, and we call these things anonymous functions, and we give them little function handles. So it's like writing an M file with all your code, and then just taking a little space to write a little function that you're going to use later on throughout the program a little bit. But you just kind of put it right in line with the code, and then you separate it by using the correct syntax. But besides that, we just kind of write it into the code. So let's take a look at an example here of this. Here is an example of a function like this. The example they use is actually a logarithm function. I don't want to do that. I want to use something that's a little less innocuous, I guess. Let's see here. All right, let's do this. Let's do a function called I don't think that sum is used by MATLAB, is it? It is. Let's not use that. Let's use sum. Okay. So here is we're going to create a function that is going to add two things together. Of course, MATLAB already does this very easily. We don't have to create a function to do this. But let's create this function anyway. And we want to do this by, excuse me, first creating this little bit of code. And this little bit of code is going to look like this. Sum equals A plus B. So that would be kind of like assigning a variable to another, to the sum of two other variables. However, that's not exactly what I want to do. What I would prefer to do is to tell this thing that I want it to add whatever numbers together that I give it. So I'm going to say the sum at x comma y, for example, I think I can do it this way. No, let's actually call it add1. That'll make it easier. We'll call our function add1. And if we do at x, and we call this x plus 1, again, I'm new to this, so it's a little bit strange. This is a particular bit of code that MATLAB knows what to do with. We have to use parentheses here. MATLAB knows that if you put an at in front of parentheses, then you're telling it that you're making a function assignment. You're saying that this new function called add1 is going to equal x plus 1 with an input of x. So I go ahead and hit return. It says that, and then I can do this. I can do add1 of 9 and hit return, and it'll tell me the answer is 10 because I've created this function inline. Created this inline function or this anonymous function, and now every time I use this, it will know. Notice that over here in the workspace, it created a file with what would they call a function handle. The function handle is add1. Add1 is the function handle. It's created this, they call this a map file. But it's created this file now that has this function stored in it. Now when I clear this workspace, it'll clear that function. That function is not saved to the computer. It's just saved in the workspace. So if I hit clear here, and then I try to use add1 of 1, it will have no idea what I'm talking about. So I have to redefine it every time. But it can be useful to do very simple functions. If I did, so if I go back to my previous one, which is the sum, let's make one that's called sum. Sum. I think I can do at x comma y. I think it'll let me do 2. And do x plus y. Let's see if it'll do that. Looks like it will. And then I can do the sum of 2 comma 3. And it'll add them together. So it's very simple. The handle is the sum, right? And the anonymous function is this code that I typed in up here. So it's a quick way to make a very, very small, very simple function that you're only going to use within, a certain realm. You're not going to use it outside of different programs because once you clear this program, it can't be used again. All right. Excuse me. All right. One other one that's kind of weird to me is the functions. What's a functions? Okay, so another advantage of this is kind of weird. They call this functions. If you want to create a function that you're going to use later, like a mathematical function, let's say like a polynomial. So let's call this poly 5, and let's let it equal at x x. So the variable in this function is going to be x, And the function is going to be something like -5 times -5 times x dot to the fifth, x dot to the fifth, right? Minus 400 times x dot to the fourth plus 23 times x dot to the third, or whatever. So this polynomial now is a fairly complex polynomial, and this is where this can be very useful. I've got this. I'm going to suppress the output of this thing, but I've now assigned this variable poly5, or this function poly5, to this polynomial. But I haven't told anybody what x is going to be. But now I can actually use this. I can actually use a new function, a new plotting thing called fplot, and I can plot this function. So I can plot the function, and I can plot it in a. I can plot the function poly5, for example, and I can plot it with values of x ranging from in a group of numbers. You know, I can go from 1 to 50, for example. I go 1, 50, put it in there, hit return. I get my fplot here somewhere, wherever my plot window is, right here, and there's my fplot from 1 to 50. Okay. So, was that the right one? Yeah, that was the right one. I could also do it from 0, or from -50 to 50, or whatever. So it's a very quick way to plot functions without having to type in that all those numbers into there, you know, and do that crazy thing. It's just a quicker way around things a lot of times. So it has a lot of uses. This idea of these anonymous functions, often called functions. But anyway, they're the same thing. All right, let's see what else can we do here. We're doing subfunctions. Yeah, do I really want to get into subfunctions? All right, well, so they actually show a couple of examples of subfunctions in the book, and I believe that's part of our homework. Let's check our homework really quick. I can't remember if I had to do subfunctions or anonymous functions in the homework. Let's take a look here. Yeah, we have them as subfunctions. Which is fine, I guess. I think I'd rather have you do anonymous functions, actually. Oh, here we go. In question 8, I have you do it in anonymous functions. In question 9, I have you do it as subfunctions. So I have you do it as both. So you can do one file with anonymous functions, 4 anonymous functions in one file. Do 4 with 4 subfunctions. Subfunctions are really just functions within functions, and that's not that big a deal, actually. Let's take a look at how it's done. So here let's open up a new function. Let's close our star function. Let's open up a new function. And here we are. Our function has a beginning and an ending, but I can actually put in here another function. I can actually type in function, and it will create a subfunction. Notice that it pushes it over, it indents it, and then if I write end right after that, it'll indent that one as well. And then I can put spaces in between there and put some stuff in between. This just means that I can have multiple functions within my function. Okay, So I can write 3 different functions, and then I can paste them all into one function and have 3 separate functions within one function. And it's just a quick way of editing things, essentially. If you've already written a function to do something and you want to put it inside of another function, you can just paste it in there. You don't have to worry about deleting anything else. You just highlight everything from function to end and paste it in, and you're good to go. They do one of these with they do one of these with the with an example of making doing squares. Oh, they do potential energy, and then they do one with they do the other. Actually, they do both of them with potential energy. In the case of the homework, you have some conversions. You're converting from one temperature value to another. So from degrees Celsius to degrees Fahrenheit, for example. So you could write one function for degrees Celsius to degrees Fahrenheit, another function for Celsius to Kelvin, another one for Fahrenheit to Kelvin, another one for whatever to whatever, and write all those functions separately, make sure that they work separately, and then you could paste them all into one function. You could just put all those functions in one function, and it would do all 4 of them together. Right? So that's really all there is to it there. There's nothing much more than that. They do have their advantages in many ways that you can, if you've got all 4 of those functions now pasted into one single function, then you could graph all those things together, or you could make some kind of thing with them all, a table with them all together, all at once. And that's the real advantage. You don't have to rewrite all the code or erase a bunch of stuff from the code. You can just cut and paste and be done. So that's kind of where that is at. I don't want to go through all that. We're running out of time anyway. But any questions at all about what we've covered? I mean, covered quite a bit today, but any questions about how the homework goes? Like I said, we don't have very many people participating in that online shared document right now. There's not very much participation on there. By now, by the end of this week, everyone should have at least 6 entries in there. And like I said, grading time is up. So as I'm grading these chapters one by one, you're getting a score for that. You're getting a score for participating or not participating. So if you want a score for participating, you get in and get at least 5 right now and 6 by the end of this week. So that when I get to your homework and I grade your homework, I look at that and I give you a score for that. Okay? Make sure you get in and do that. Make sure you get in and enter in your class notes as well into your homework. Any other questions, concerns, or comments, or anything else?
I honestly haven't gone to the blog.
Yep.
I started the assignment. I finished 1 and 2 when I stopped at 3. But it's because there's a part that's confusing, and also I'd say time to do this week.
So let's go over this one more time here really quick. When you go into your homework, when you go into the weekly assignments, the first thing you do every week is open this thing. And that's where you put in your tips, tricks, and everything else. And right now I've got 5 from one student, 1 from another student. And then the examples up here. These are all examples. So I really should see 5 from each student, and you can put them all under one date if you want. That's fine. You don't have to backdate them or anything. Put them all under one date, and I'll score them as 1 for each week, and that's fine. But you should go into this first every week and put down your tip, trick, or whatever, your function that you discovered. As long as nobody else has written it down, you can write it down. And then you go into your homework. And when you go into your homework each week, you will find different questions. The first question in all the homeworks, I think, is the notes from class from that week. So there should be an M file of all the stuff we did in class, all the functions that we ran, all the programs that we wrote, and you should have an M file that has all that code written with your notes, comment lines with your notes in there of the things that you learned. while you're doing that, things that you were thinking about doing that. Then, the rest of the questions will be problems that you have to solve. In this case, there's only one more question with 6 problems in it. In the case of this week's homework, there's many questions because each question has one separate problem in it. So, and then you upload your M files of that code. I don't just want a copy of what you type into the command window. I want an M file with your code in it. I don't want the results of your code. Okay? That's easier for me. Now, if you do send me just a copy of the command window with all the results, that's okay when we're starting out, because I understand getting it right and understanding how to do this is a little difficult when you're first learning how to code on a computer. But eventually, I want you to understand that I want an M file, a .m file, that just has your code in it, that I can actually just hit run and watch that code execute. Okay? So, and between each problem, you should probably have a pause so that I can watch one execute and then hit a key and watch the next one execute, and so on and so forth. Just like we mentioned in, I think, the first or second class. So, did that answer your question?
Yeah.
Okay.
I wasn't really sure how, because I did save the M file, and then when I reopened it, it had all the bottom.
Yeah. In that case, did you copy it out of your command window and put it in that file? No. You just typed it in. You may have hit run and then saved that. That's possible. Yeah. Just try to save the code though. That's best for me. It just makes it much easier for me to see what you've done. I can do it either way. It just takes me longer to do it the other way.
Yeah.
All right.